39 kilometers. That is the distance between the English coast at Dover and the French coast at Calais, measured across the surface of the water. For most of human history, that gap was enough. Enough to keep two of the most powerful nations in Europe separate, enough to determine the outcome of wars, enough to shape entire economies around the fact that crossing it required a ship and a willingness to deal with whatever the English Channel decided to throw at you on a given day. The busiest shipping lane in the world, 22 miles of freezing, unforgiving water. A natural barrier so complete that for 200 years, engineers kept proposing to tunnel beneath it, and the sea kept making the idea look insane. The first serious plan appeared in 1802. Horses and oil lamps were the proposed technology. Albert Mathieu, a French engineer, sketched a tunnel ventilated by chimneys poking above the water. It went nowhere. In 1880, they actually started digging, boring a test tunnel from the English side before the British government got nervous about military vulnerability and shut it down. 4 separate attempts over 2 centuries. Each one stopped not by geology, not by engineering, but by politics, money, and the fear that connecting England to the continent was a strategic mistake. The sea always wins until the day it doesn't. In 1986, the British and French governments finally agreed. 2 nations, one enormous risk. Eurotunnel was created as the private consortium that would finance, build, and operate the crossing. No government money, private capital only. A budget set at £4.7 billion, a deadline of 1993, and a scope that had no precedent anywhere on Earth. They were not just building a tunnel. They were building 2 rail tunnels and 1 central service tunnel, running parallel beneath the English Channel, connecting 2 of the most economically significant cities in the world. The engineering was going to be extraordinary. What nobody fully admitted at the start was that the finances were going to be catastrophic. Stand at the white cliffs of Dover and look south. What you are looking at is the problem. The English Channel is not just water. It is water sitting on geology that changes radically depending on exactly where you drill. Get the alignment right, and you find chalk marl, a layer of rock that is hard enough to support a tunnel and mostly watertight, the closest thing to perfect tunneling ground that this stretch of seabed offers. Get it wrong by a few meters upward, and you hit porous rock that the sea pushes straight through. Get it wrong downward, and you hit a layer of soft clay that would seize a tunnel boring machine in place and refuse to let go. The target layer was 20 meters thick, sitting 75 meters below the surface of the English Channel. Years of seabed sampling and geological survey work narrowed the route down to the only alignment that kept the machines inside that 20-meter band for the full crossing. Every meter of deviation was a potential disaster. There was no margin. The engineering started before the machines went underground. On the English side, the cliffs of Dover presented an immediate problem. You cannot launch a tunnel boring machine from the face of a vertical chalk cliff. The land had to be prepared first. 250,000 cubic meters of rock were removed from the cliff face using controlled demolition, blasting out a flat working platform directly into the legendary white chalk that had defined the English coastline for centuries. A new piece of Britain was made from dynamite and necessity. On the French side, near the village of Sangatte, engineers took a different approach. They excavated a massive circular pit 60 meters deep, sinking it into the ground near the coast so the tunnel boring machines could be launched underground rather than from an exposed surface. 2 countries, 2 geologies, 2 completely different construction solutions, all working toward the same point beneath the channel floor. The machines themselves were not purchased off a catalog. They were manufactured. 11 tunnel boring machines, each one a self-contained underground factory designed for the specific conditions of the English Channel crossing. The cutter head of each machine weighed 600 tons. In front, a rotating face of tungsten carbide disc cutters ground through the chalk marl, cutting a clean circular profile. Immediately behind the cutter head, hydraulic arms lifted prefabricated concrete tunnel segments into position and pressed them against the tunnel wall, sealing the ring before the next advance began. The segments were watertight. They had to be. They were the only thing standing between the workers inside and the full weight of the English Channel pressing down from above. The United Kingdom launched 6 machines, 3 for the land section running inland from the coast, and 3 for the sea section boring out beneath the channel. The French machines were different in design. They were sealed face excavators, pressurized to resist the wetter, looser rock conditions on the French side of the channel, where the geology was less cooperative and groundwater pressure was higher. The temperature inside these tunnels, unventilated and deep underground, could reach 50 degrees Celsius. The French machines operated in conditions that amounted to a pressure cooker, miles from sunlight, boring forward through rock that was actively trying to flood around them. The service tunnel went first. This was the strategic decision that shaped the entire project. Before either of the main rail tunnels could be driven, the smaller central service tunnel, 4.8 meters in diameter, compared to the 7.6 meters of the rail tunnels, pushed ahead to sample the ground, detect water seepage, and establish the geological conditions that the larger machines would follow. Every meter of the service tunnel was a gamble with early warning value. Water seepage was the signal everyone feared. Any leak had to be found immediately and grouted shut before it could grow, because a small leak in chalk marl at 75 meters depth does not stay small. The service tunnel crews were working in the earliest warning system the project had. Massive flooding could trap entire tunnel boring machine crews and end sections of the project permanently. The pressure was not just geological. It was on the schedule, the budget, and the lives of the people underground. To stay inside that 20-meter band of chalk marl across 39 kilometers of seafloor, the machines needed guidance of a precision that the construction industry had rarely been asked to deliver. A laser beam projected ahead of each machine gave the operators a visible reference line to steer by. The primary guide was a gyroscope, an electronic compass that tracked every rotation and deviation and fed corrections back to the operator. Steering a 1,000-ton machine through solid rock is not like steering a vehicle on a road. The corrections are slow, the consequences of error accumulate over hundreds of meters, and there is no ability to reverse and try a different line. The operator worked with sensor data and experience, nudging the machine onto course fractions of a degree at a time, trusting instruments in total darkness to keep the alignment inside a target they could never see. The logistics of what came out of the ground were as demanding as what went into it. 7.5 million cubic meters of spoil, the chalk and clay and rock removed by the boring machines, had to go somewhere. On the British side, the decision was made to dump the material into the sea at the base of the cliffs, contained behind a seawall. The spoil accumulated until it had formed a new 90-acre coastal platform at the foot of the Dover Cliffs, a piece of land that had not existed before the tunnel was dug. The English Channel was physically pushed back. When you do not know where to put the dirt, you build an island. The geography of southern England was permanently altered by what came out of the ground beneath the channel. After months of advance, the service tunnel reached its critical moment. 39 kilometers of boring from both sides, the British machines pushing south from Dover and the French machines pushing north from Sangatte, converging on a meeting point 75 meters below the surface of the English Channel that neither team could see, guided only by gyroscopes and mathematics. The final alignment check before breakthrough used a pilot hole drilled through the last meters of chalk. On December 1st, 1990, the pilot hole broke through. The two teams met. Workers shook hands beneath the English Channel for the first time in history. The alignment error across 39 kilometers of blind boring from 2 separate continents was less than half a meter. That is not good engineering. That is something closer to impossible precision, delivered under conditions that made precision almost impossible to achieve. The main rail tunnels followed the service tunnel over the next months, their larger machines cutting the final profile that the trains would use. The rail tunnels had to be built to tolerances that the service tunnel, impressive as it was, could not fully prepare the teams for. High-speed trains generate aerodynamic effects that are violent in an enclosed tunnel. When a train traveling at speed enters a confined tube, it pushes a wall of compressed air ahead of it that creates pressure waves capable of damaging the tunnel structure and the train itself if the geometry is not exactly right. The track within the tunnels was precision, welded for high-speed operation. Every joint, every curve, every gradient was specified and checked against the behavior of trains that would eventually travel at up to 160 kilometers per hour beneath the sea. Then came the question of what to do with the tunnel boring machines themselves when the job was finished. The French machines could be recovered. They were extracted and brought back to the surface. The British machines presented a different problem. 6 enormous machines, each weighing close to 1,000 tons, sitting at the end of 39 kilometers of finished tunnel with no practical way to turn them around and drive them back. The decision was made to seal them in place. The British tunnel boring machines that built the Channel Tunnel are still there, buried beneath the English Channel, entombed in chalk at the end of the drives they completed. A 1,000-ton engineering tool sacrificed to save the time it would have taken to remove it. Somewhere beneath the seabed, the machines that built one of the greatest engineering projects of the 20th century are still sitting exactly where they stopped. With the tunnels bored and the linings in place, the fit-out began. The Channel Tunnel is not a pipe with tracks in it. It is a complete transportation system built inside 3 parallel tubes. Giant fans were installed to push fresh air through the full length of the running tunnels, cycling the atmosphere continuously. A failure in ventilation inside a sealed underwater tunnel is not an inconvenience. It is a catastrophe. The air handling systems were designed with redundancy on top of redundancy. Power and signal cables were run the full length of the tunnel to supply the 25,000-volt overhead lines that the electric trains would draw from. Every 375 meters, a cross passage connecting the service tunnel to the rail tunnels was built and fitted as an emergency escape route. The service tunnel that had led the boring operation now served its permanent purpose as the lifeline of the system. A fire in a train tunnel requires every person aboard to reach the service tunnel within minutes. The entire safety logic of the Channel Tunnel depends on that connection being accessible and functional at all times. The terminals at Folkestone on the English side and Coquelles near Calais on the French side were built as massive logistics hubs, effectively small cities designed to move cars, trucks, and coaches onto the Eurotunnel shuttle trains. The loading system is unlike anything that existed before it. Vehicles drive directly onto purpose-built rail wagons and are transported through the tunnel in 40 minutes, enclosed in the wagons for the full crossing. It was described at the time as a high-speed underground cruise, and the description is accurate in the sense that passengers stay in or beside their vehicles for the entire journey, the tunnel doing everything around them. The project opened formally on May 6, 1994. The cost had grown from the original estimate of £4.7 billion to £9.55 billion, nearly double. The engineering had been delivered. The finances had been a disaster from the first year of construction, overrun after overrun, absorbing the private capital that the consortium had raised to build it. 11 workers died during construction. The human cost, the financial cost, and the political cost of 2 governments managing the relationship between a project this size, running this far over budget, were all real and significant. The impossible had become reality, but the price of making it real was far higher than anyone had admitted when the contracts were signed. 2 years after opening, the greatest fear was realized. A fire broke out inside a truck shuttle inside the tunnel. The fire suppression systems activated. The cross-passage doors sealed. The passengers and crew reached the service tunnel through the emergency escape routes. Every person aboard survived. The safety system that had been designed for the worst case performed exactly as designed under the worst case. The 3-tunnel design, which critics had called over-engineered and expensive, proved in a live fire that it was exactly right. With the completion of High Speed 1, the dedicated rail line connecting the Channel Tunnel to London, the journey time from London to Paris fell to just over 2 hours. Faster than flying when you account for the time spent at airports, the security lines, and the transit to city centers. The tunnel that took 2 centuries of planning and a decade of construction to build now moves 10 million passengers per year beneath the English Channel, in trains traveling at speed through chalk that the sea spent 200 years insisting could not be crossed. The physical link is permanent, an unbreakable bond of steel and chalk, 75 meters below the surface of the English Channel, built with a precision that still makes engineers who study it stop and think. They said the sea was a wall. The Channel Tunnel is the proof that the wall was always just geology, and geology can be solved. That is what humans do at their best. Like, share, and subscribe for more.